Saturday Morning Physics is sponsored by the Physics Department of the University of Michigan, by the Dr. M. Lois Tiffany Endowment, and by gifts from friends of the program.
Now, what I will do today is basically bring us on a time travel to the edge of time, near a few million years after the Big Bang, and try to find out how these black holes that we see today in galaxies were formed and evolved along the whole cosmic time for 13 billion years or so. So let me give you an idea of the outline for today. I will review again some of the properties of black holes. I will focus on these massive black holes, millions to billions of solar masses that reside at the center of galaxies, starting from the Milky Way, but we see them also in other galaxies. Then I will move back in time, a bit of cosmology, looking at how we can find out how these black holes formed very, very early in the history of the universe. And then I will show you how these black holes grow in time and until we can see now them in the center of galaxies. Now, I'll use very often in my slides the acronym MBH, which means massive black hole. And if I use some other acronym that I haven't defined, please just let me know. Okay, let me start with the definition of black hole. Well, a simple definition for a black hole is an object which has an escape speed which is larger than the speed of light. In other words, the inside of a black hole is invisible. The reason is that if you're sitting on a black hole, well, it's kind of hard, but you can try, and you want to communicate with your friends on a different planet, it's very hard for you, actually it's impossible for you to send them a message. So I will try here an experiment, and you want to send a message to your friend who is living on Mars. So you have to send your message very fast, so that it can leave the gravitational attraction of Earth and go all the way to Mars. So let's try some experiments. Suppose that you can send your bottle, your message bottle, at a speed of 2 kilometers per second. What happens? Nothing. You're not strong enough. Now, second, it seems a very small number, but it's faster than a bullet shot by a rifle. It's faster than the faster aircraft available right now. So actually, to leave the Earth, you have to go pretty fast. Even if you go at 7 times the speed of a bullet, you're still crashing onto the Himalaya. To go all the way to your friend who is living on Mars, you have to go at about 11 or 12 kilometers per second. So this is a very large speed, and at this point your bullet escaped into space, actually never to return. But still, this is a very, very, very small velocity compared to the speed of light. The speed of light is 300,000 kilometers per second. So now if you are inside a black hole, you just cannot send any message outside. So that's why black holes are invisible. What is the other property of black holes? Well, black holes are, in my opinion, are fascinating because they are the simplest objects in the universe. What do I mean by simple? Well, they are characterized by only 2 properties: mass and spin. Mass, their weight basically, and spin, how fast they rotate around themselves. Now think of it as a comparison with how hard it is to describe a person. You have to say someone's height, the weight, the color of the hair, how many hairs on the head, how many fingers, the length of the nails. For a black hole, you just use two numbers, mass and spin, and that's it. No problems with DNA and the social upbringing. That's very easy. So it's simple to understand mass. Mass is just how much an object weighs, but why do black holes spin? Well, this has to do with how black holes get their mass. So now this is a black hole. It's a colorful black hole. It's very nice. And now we will mimic what happens when we throw some particles onto the black hole. We can imagine that we're sending them towards the black hole in a given direction. So now we're shooting particles, well, here, towards the black hole. And you see that it starts spinning. It's very easy. Now, what happens if we shoot particles in the opposite direction? You see that slowly the black hole stops spinning, and given enough air or enough particles, the black hole will start spinning in the opposite direction. So we see that the spin of a black hole is linked to the way it interacts with the outside. Now, thanks. So how do black holes get their mass? Well, they're just eating. Black holes are known for being gluttons. They eat quite a lot. Especially they ate a lot of food, which is hydrogen and particles actually, when they were young. Teenagers tend to eat quite a lot as well. So today we will see the infancy of black holes and their phase of being teenagers. So we will see a lot of black holes eating food. And it's important to see that black holes eat food because that's when we can spot them. So let me first give you a couple of units of measure. The reason is that I tend to lose memory, so I will always use these words that are keywords for me, but you haven't maybe heard of them very often. So when I measure the length or the distance between objects, I will use this word, which is a parsec. A parsec is just the units of measure that we use in astronomy, and it corresponds to about 200 times the distance between Earth and Sun. And it's about a few light years. The other distance that we use indeed is the light year, which is the distance traveled by light in 1 year. And it's only 63,000 times the distance between Earth and Sun. Mass. Whenever I talk about black holes, you will see that I will say their mass in units of solar masses. Well, that's a very good way of saying it because you can just see how many suns you can stick inside the black hole and see how big that is. So typically we use the mass of the sun, which is about 1 million times the mass of Earth. So these black holes are pretty heavy. As I said, millions to billions of these solar masses, of the masses of the sun. And the third unit of measure that I will typically use is the luminosity, how bright an object is. And again, I will use the sun as my unit of measure, so everything will be in units of the luminosity of the sun. So let's do a first experiment right now. Let's look at our own galaxy, at the Milky Way, and express its properties as a function of these units. So this is a cartoon image of the Milky Way in which I show the main characteristics, the size, the length is about 10 of these kiloparsecs, or a few 10,000 light years. The mass of our galaxy is about 10 to the 12 solar masses, which means that it contains more or less 1 trillion suns in terms of mass. And still, it's not the biggest galaxy that we have. And the luminosity of the galaxy is about 10 billion suns. So we see here that we have a bit more mass than luminosity. So on the top, you see a face-on view of the galaxy. On the bottom, you see an edge-on view. So you see that there is a disk, which is here shown in green. It's made of gas and stars. You have the central region, which is very bright, which is called a bulge. And it's made mostly of stars. And then you have everything surrounded by a spherical object, which is called a dark matter halo, which is dark because it's made of this unknown dark matter. But I think that Professor Gnady next week will talk much more about dark matter. So for now, we'll just leave it as a hint that in our galaxy, we have a lot of mass which is not made of stars. But we will focus today on what lies at the center of galaxies, at black holes. The way black holes were discovered was not as black holes proper. So there were hints that some objects which were so massive that would be crushed inside a point were made theoretically, more than 200 years ago. But the discovery of some objects that would defy every other description of bright luminous matter we know about came at the end of the 60s, in 1967, when they found these very special objects that they called quasars, or quasi-stellar sources. So this is an example. This is actually M87, which is a galaxy very nearby in the center of the Virgo cluster. It's a very beautiful galaxy. It's huge. It's one of the biggest galaxies we've ever seen. And from the center, you see this sort of jet shooting out. So if you look at the center from which this jet comes from, it's a very small source. At any telescope except for the Hubble Space Telescope, it looks like a point source. So generally, you would call it a star. But unfortunately, they cannot be stars. Why? Well, because they are as luminous as galaxies. So you have the luminosity of a whole galaxy compressed into the size of, slightly bigger than the size of a star. So let's go through the train of thoughts that led astrophysicists in the 60s to think that quasars are powered by accreting massive black holes eating lunch. So they are as luminous as galaxies, but they have these characteristics of having the brightness varying on very short time scales. So they become dimmer and brighter on time scales of a week. So here you see an image of these light curves that tells you how brighter or dimmer than the average a quasar is. You see here the time is in days. So you see how the brightness of this object changes by a factor of 100, 200 within a week. That's a very, very fast behavior. So now you can also assume that you're looking at this object and the brightness changes because light is traveling throughout the source. Now, that makes things a little easier because you know that what you're observing is light. Light has the good characteristic of moving at the speed of light that we know very well. So if you measure the time it takes for light to vary between one side of the source or the other, and we have seen in the previous plot, it was about a few days, about a week. So you measure the time, you measure the speed of light, you can derive how large the object that caused the change in light is. Since the emitting region is less than 1 light week, then the size of this galaxy is about 1 light week. 1 light week is, if we remember the size of the Milky Way, is about 1 million times smaller than a galaxy. It's about the size of the solar system, a few times the solar system. So these objects just cannot be galaxies. They are as luminous as galaxies, but they are as large as the solar system. So the astronomers had to come up with an alternative theory. So I will try to prove you that black holes are powered by black holes accreting matter. How will I do that? Well, first I've proved you that these quasars are not galaxies, and now I'm going to prove you that these quasars are not stars. Well, first of all, you already know kind of half of the answer. These objects are as luminous as galaxies. Now, you measure the luminosity, and I think all of you have heard of Einstein's equation, energy is mc squared. So you can apply this relationship to find how much energy and how much mass you have in these objects. Actually, the luminosity of an object can be expressed as the mass times c squared, so the energy, divided by the time. So it just tells you how much light you see at every second you stare at the source. And then there is this factor epsilon that just tells you how efficient an object is at producing radiation. For stars, we know that this epsilon is a very well-known number, and it's about 0.7%. So if you assume also, you look at how, the lifetime at these quasars, you can derive it very simply by looking at how many you find in the universe. The lifetime is about 10 to the 7 years, that is 10 million years. With this, you have all the information to find the mass. And the mass of these objects is about 100 million solar masses, 100 million suns. So there is no possibility that a star that massive exists. If a star that massive existed, well, it would turn into a black hole. So all lines of reasoning are telling us that these quasars are powered by supermassive black holes with masses of millions to billions of solar masses. And now, en passant, the efficiency with which a black hole takes matter and transforms it into light is the highest efficiency that we have in the universe. So if we could ever build an engine that could use the same power that black holes use, we will save a lot of energy for Earth. But if you have to create black holes, to go to a black hole to form energy, it will be kind of a rough trip. So for the moment, we have to be happy with the new advances with energy on Earth. So now, I think I've proved you, and I think that Doug did the same proof last week, that supermassive black holes with such big masses exist in the universe. And the next step is to wonder how they got there. I mean, you can be a fairy and say black hole, but it doesn't really work. So we can try and find out different ways of forming supermassive black holes as a function of the physics that we know. Let's start with what we know very well, stellar mass black holes. So black holes with masses of a few solar masses are very well known to exist. They're not a big deal. They're predicted to form as the end point of the life of stars, which are about 10-50 times the mass of the sun. So they're very natural, very normal in astrophysics, but they're tiny. There are a few, the mass is at most 10 solar masses. Well, the black holes that we're talking about in quasars have masses of millions of suns. So this image shows you a comparison between the masses of some black holes that were found in galaxies. This is based on work that Professor Richardson did. So here you see a compilation of galaxies on the left-hand side, and on the right-hand side we're zooming in the center and looking at the very center where we expect these black holes to reside. And the dark points show the size of these black holes in terms of a uniform scale. So you see that some galaxies host black holes that don't even fit in the slide, while some galaxies host black holes which are a little smaller. So you go here, the masses go from 3 million suns all the way to 2 billion suns. So we have to find a simple, unified theory to explain the evolution of all these objects. So the first step would be to look at images of the universe and look at galaxies and black holes. Now, these are two of the deepest images of the sky that we have, meaning that here we are seeing an enormous number of objects. Now, here these are two deep fields. One is taken with Hubble, the Hubble Space Telescope that observes optical light, what we can see with our eyes. So on the left-hand side, what we're seeing are galaxies, millions of galaxies. Stars, you're seeing starlight. On the right-hand side, this is the Chandra Deep Field. The Chandra Deep Field doesn't observe in optical, the Chandra Telescope doesn't observe in optical. It observes in X-rays. So it's looking at the bones. It's like doctors looking at your bones. So it's a completely different wavelength. And in X-rays, what you actually see are accreting black holes, are quasars. So on the right-hand side, every point, each one of that red points is a quasar, is a black hole. There is a black hole in there. Now, if you were to count carefully, you would see that for each quasar, you would find about 100 to 1,000 galaxies. This means that we have more galaxies than quasars. Now, the next question is very simple, and it's, so is it so? Do we see more galaxies than quasars because only some galaxies host black holes? And these black holes are quasars, so they are eating lunch for the whole time? Or do all galaxies host a black hole, and this black hole becomes a quasar, starts shining only every now and then? So this has to do with the distribution of black holes in galaxies. This has to do with the physics that put these black holes in the center of galaxies. So we have to go back in time and put these objects in a cosmological context to understand how this worked. Now, what you actually, if you were an observer, what you wanted to do is to take a picture of these galaxies in which you could see all the black holes in there. Those that are quasars and those that are not. Those that are eating food and those that are just starving. Now, that's pretty much wishful thinking, because looking at black holes, it's hard. So we have seen that black holes are black in the sense that they're invisible. They do not shine because they trap light inside them. So how can you see black holes? Well, this is, as I said, work that was pioneered by Professor Richardson, by Doug. The idea was to look at the center of galaxies. We expect that the black holes sit in the center of galaxies. And what you want to do is really to look at the gravitational effect that black holes have on the surrounding stars. Now, black holes are massive, millions to billions of suns. And they're very dense, very compact. They have the size of, well, basically the solar system. So they have a very strong gravity. So in their neighborhood, they will force stars to move around them. But when I say the neighborhood, well, it's a very, very small region. So just to give you an idea of the scales that we are dealing with. So this is a galaxy. This looks pretty much like the Milky Way. It's not the Milky Way, but it's very similar. The size is about 10 to 50 kiloparsecs, so it's huge. Now, let's zoom in the center. Let's zoom in by a factor of 1,000. So if we go from kiloparsec size, kilo means 1,000, to size of 1 to 10 parsecs. So the size of this size is about 200 times the size, the distance between Earth and Sun. Here you're seeing a lot of stars. The center of galaxies is very full of stars. Now you have to look at the motion of each of these stars and see if they're moving under the guide of a black hole or under the guide of the whole galaxy. Now, even if you do this, you have to really be able to observe the very little center of a galaxy. This is very hard. This is something that can be done for only about 40, 50 galaxies in our neighborhood. Now, if you wanted to look at actually the black hole itself, this object which has the size of the solar system, well, you have to zoom in by another factor of 10 million. For the moment, it's kind of impossible. But we never know where science is going. So this type of research, type of work, was done for the first time for our favorite galaxy, the Milky Way. Look at here. Here, scientists have traced the motion of stars around the Milky Way, the center of the Milky Way, for many years. Now, what you see here are stars moving around. The way these stars move around the center is very similar to the way planets move around the sun. This is a Keplerian system. Kepler laws apply here. Now, the center of this system is not a sun. the center around which everything revolves is this fake star over here. This star was put by hand while making the movie because the center is dark. You cannot see anything down there, but you can measure a mass of 4 million suns. So what is very massive and completely invisible? Well, a black hole. So this was the proof that we have a black hole in the center of the Milky Way. Its mass is 4 million solar masses. So that was the very first time that we can prove without any doubt that we have supermassive black hole in the center of galaxies. Now Professor Richardson and other groups went on and tried to measure the masses of these black holes in the 40 galaxies in which this process can be done. And they found something very unsuspected, unusual, interesting, fascinating. I'm still amazed at this discovery. So they found not only that black holes exist in galaxies, but black holes and galaxies know about each other. So if you measure the mass of black holes and you measure the mass of the bulge of galaxies, the spherical part in the center, you find that the mass of the black hole is 1,000th of the mass of the bulge. So they have evolved together. Galaxies know about black holes know about galaxies. So now, why is this so amazing? The reason is that if you look at a galaxy has a size of 10 kiloparsecs. But the black hole sits in the very central parsec. So how is it possible they can communicate with each other? Well, this is what we'll discuss at the end of today's talk. But for the moment, we can say for sure is that if galaxies know about black holes and black holes know about galaxies, they must have formed or co-evolved together throughout the cosmic time. So our trip for the next few minutes will be to go inside here and go back in time and see how we can make a massive black hole. Just use physics that we know to make black holes. Now, you need some information to start your theoretical model, to start to think, scratch your head, and think about how to form a black hole. Some of the information that you need is when black holes existed for the very first time. Okay, so let's take our time travel machine. Our time travel machine is a simple telescope. Nothing, particularly crazy. In fact, if we're just looking at faraway objects, since light travels at finite speed, the more far away you look, the more far away in time you're looking at. So if you're looking at the sun as it is now, you see it as it was 8 minutes ago. If you're looking at the edge of our Milky Way, you will see it as it was 32,000 years ago. So if you look at a galaxy or a black hole or a quasar, which is very, very, very far away from us, billions of light years, you are seeing this quasar when the universe was very young. You're seeing this object as it was several billion years ago. So if you look at quasars that are being detected at very large distances, actually quasars are the objects that have been detected at the most distant objects today, we're seeing them in the infancies when the universe was very young. Really, really young, when the universe was still in kindergarten. So we can apply a simple relationship. We know that light travels at the speed of light. We measure the distance at which we see a galaxy or a quasar. We can find how long it took light to travel from this object to us. So we do this for some quasars. We measure the distance, and we find that these quasars existed 12.9 billion years ago, almost 13 billion years ago. And how old is the universe? 13.7 billion years, as Doug said exactly last Tuesday. So when you're looking at these quasars, we're looking at objects that existed when the universe was very, very young. Now, what is another mystery here? Well, it's still an unsolved mystery. The black holes that are powering these quasars, that are sitting in the center of these quasars, are as massive as the most massive black holes that we see today. So black holes that were still in kindergarten were already as tall as basketball players. This is something that, they had a very accelerated growth. They were growing much faster than we typically expected. So now we know that quasars and black holes are cosmological objects. They were formed soon after the Big Bang. We expect just a few 10 millions of years after the Big Bang. So let's introduce a little bit of cosmology. Let's look at how our universe evolved with time, and let's see where black holes fit in all this. So now this is a sketch of the evolution of the universe from the Big Bang all the way to now. Now, this is a sketch, but it has some interesting points. So each of these smudges is a galaxy. So what you should notice here is that the galaxies today are much bigger than the galaxies that existed down there. We say that the universe is evolving in a hierarchical fashion, from small to big. In fact, we can see a cosmological simulation. What I will show you in a minute is a movie that shows the evolution of a piece of the universe from very early times, from when the universe was very young until today. Now, what you should pay attention to is the size of the galaxies in this simulation. You see how the sizes of the galaxies, which are these balls, increase with time. Let me go back and show it again. You see you're going from small galaxies to big ones. That's why we call this a hierarchical growth. Small galaxies form first and they grow. How do they grow? By merging together. You take a lot of small galaxies, you put them together, and they form a big galaxy. So if black holes are cosmological objects, they have to evolve with their hosts. They have to evolve in a hierarchical fashion as well. They have to be formed at the center of protogalaxies, and they can evolve with time. So I will now discuss with you some of the paths to black hole formation. Now, this is research which is being done right now. So we do not have an answer yet. We are looking for the answer. I'm showing you some proposals, and maybe you can vote for your favorite one. So this is the first theory, that black holes are created by a few mass with a very intense bitterness. I'm not sure I buy this theory, but I think that by experience, sometimes this can be true, at least on small scales. In cosmology, we have to think of some different theories. Now, let me show you some examples. So I will show you 3 different ways we can form black holes. As I said, we can take in the end a vote for your favorite. So the first way of forming a black hole has to do with the formation of the very first stars. Now, here we're looking at a galaxy when the universe was 10 million years old. A galaxy back then was as small as 1 million times smaller than our Milky Way today. It was a tiny little object. It was composed of dark matter, so this unknown material which is permeating the whole universe, and gas. Gas is hydrogen, well, air, basically. The theory is that you can run some simulations that show you the evolution of this system. And what you see is that if you wait some time, at the very center of this galaxy, you have the formation of one star that explodes very fast and leaves a black hole. Now, why do we like this theory? We like this theory because it's very natural. It's the same physics that we have for the forming stellar mass black holes today. The difference here is that the first stars are supposed to be very massive, 100 or 200 times the mass of the sun. So the black holes that they leave behind are pretty massive too. Now, what it is that we do not like about this theory is that we do not know if the very first stars were indeed massive enough to form these black holes. So this is a theory that we still have to prove, in the sense that we have to look for the very first stars or the signatures of the very first stars and see if they could make massive black holes. So a few years ago, basically in 2005, since I was not sure about this theory, with a couple of collaborators, including famous Martin Rees, as Fred says, we scratched our head and we tried to come up with a different series of models. So this is another one. So this is the first one that we came up with. And the idea was, okay, let's take again a protogalaxy. So it's again this ball of dark matter and this ball of gas. Now let's spin this gas a little bit. If we spin gas, what happens? If I spin fast this spherical object, it flattens down. So let's look back at our galaxy here. Yes. We are spinning this galaxy. The gas in the galaxy is compressing, and it's forming something that we call a disk. Well, a disk is a flat rotating object, what we were seeing over here. So, but for some of these galaxies in the very past, in the very far away past, the process of collapsing these disks was very unstable. What it means by unstable, that you couldn't stop the object from collapsing to the center. You are just keeping the gas going in towards the center, toward the center, so you increase the gas density all the way until you reach a phase in which the gas turns into a black hole. You are able of reaching the densities at which you do not have gas or normal matter, but you squeeze everything inside a black hole. Now let me show you a little movie. So here, in this movie, you will see a simulation of one of these unstable galaxies. So look at here, you have this protogalaxy. You see the size of this galaxy occupies the whole slide. Now this disk is unstable, so that it collects, it contracts everything towards the center. See how small it's becoming. And if we wait long enough, you will see that basically all the matter disappears towards the center. So we expect that these disks can become dense enough that they can turn into black holes in the center. But still, I was not happy about having only two models for the black hole formation. So I thought, okay, what happens if this gas that is going down toward the center doesn't form a black hole, but forms stars? Well, in the center of galaxies, we see stars, don't we? So maybe we have to form stars before we form black holes. So we go back to our galaxy, and we again have our gas falling towards the center as we were seeing before. But now we can assume that some of this gas actually doesn't become a black hole, but forms a cluster of stars. A cluster of stars is a very dense ball of stars. It's very similar to what we see in the center of the Milky Way. And it's so dense, there are so many stars in such a small region that stars collide one against the other, merge together, until in the center, instead of having 1,000 small stars, you have one big star that weighs about 1,000 solar masses. And what happens to this star? Turns into a black hole. So these are just three different ways in which you can take your protogalaxy. You start from just gas and dark matter, what you expect to be pretty common in the early universe. And you can turn some of your gas and some of your stars into black holes. Now, what is the good thing about this, any of these models? Is that you form black holes at very early times in these very small protogalaxies that existed 10 million years after the Big Bang. And so you have plenty of time to grow them to become supermassive empowered quasars later on, when we actually spot them. So how can we actually grow these black holes? Is it possible to form these tiny little black hole seeds 10 million years after the Big Bang and have them become supermassive black holes by today? So how can we grow our little black holes from seeds to beautiful flowers? So here, just to show you that we start from the tiny black holes that we start with, well, they're tiny but not so small, are about 10 million times the mass of the sun. But the black holes that we see today in galaxies and we see powering quasars have masses that go from 1 million to a few billion solar masses. So you see how we have to grow these black holes by large amount before they're ready to go out and become quasars. So the idea is that these black holes grow with time in the same way galaxies do. So in this picture, I just showed you again the little movie that shows the growth of galaxies in the universe as a function of time. And here I selected just the merger history of one galaxy, like the Milky Way. Basically, this is the family tree of the Milky Way. I put here a real tree just to show you why we call these trees. So this is the Milky Way today, and then these are the two parents of the Milky Way, and we can go back to the grandparents all the way up until we get to these proto-galaxies that existed a few million years after the Big Bang, where we expect some black holes to be formed. Now, these little black balls in galaxies are my attempt to draw black holes. So you see here, the black hole starts inside galaxies very early on in time, and then they follow their host. They're embedded in the nucleus, in the center of galaxies, and so they have to grow along this whole cosmic history, along the merger history of galaxies. They're connected to their hosts. So throughout this history of merging galaxies, how do black holes grow in time? Well, they grow through these two processes. One is just mergers. You take two galaxies, suppose that each of these two galaxies have a black hole in the center. You smash the two galaxies together, and eventually also the two black holes will smash together, will merge and form a more massive black hole. Now, during this phase, we expect to be able to spot black holes because of their emission of gravitational waves, because of the way they stretch space-time at the time of their merger. Another phase in which black holes grow in mass is when they become quasars. We have seen that quasars are basically black holes that are accreting matter. They are eating lunch. So let me show you how a black hole can eat lunch. We have an example over here. So this is the lunch for the black hole. It's waiting for the black hole to start. And this is the black hole, which is ready to eat its lunch. You see how the small marbles reach the black hole. In principle, we should see them traveling faster and faster. When they reach near the black hole, they travel almost at the speed of light. At that time, since they're traveling so fast, they're very close to becoming energy. So when you actually have marbles, when you have particles that are being accreted by the black hole, they're glowing very, very brightly, because part of their matter becomes energy. Energy is mc squared. Your mass moves at the speed of light, so some of your mass becomes energy. So that's how we see black holes when they're eating lunch. We see when black holes become quasars. We see the marbles lighting up in this accretion disk. So this is how we can detect black holes. Basically, we can see black holes every time they're increasing in mass, either by merging with another black hole or by eating some matter. So we can see black holes when they become quasars or when they're merging with other black holes. So this is a case of a double quasar. It is called NGC 6240. I'm learning some names of galaxies. I'm very proud of that. And here you see two quasars at the center of the same galaxy. So we expect this object, which is a quasar right now, these black holes are eating, we can see them, is the precursor of a real merger between black holes. This is, here I show the merger of two black holes, and what you see here are the ripples in space-time created by gravitational waves. And I will show you a movie about creating these waves in a minute. So, one black holes are quasars, then become, well, first of all, very pretty. This is an image created by a combination of X-ray and radio. So here you're seeing the central black hole, which is accreting. Well, you can actually see it. It's very, very tiny. It's the size of a solar system. While you see here the size of this outflowing material and outflowing radiation, that is the size of a galaxy. So when we study quasars, here is another jet coming from a quasar. We can learn about what type of food black holes like to eat, how often they eat, and when they prefer to eat. And it seems that black holes really like eating when galaxies are merging. So this is simulation. Also, Doug showed some simple example like this of two merging galaxies. These are two spiral galaxies. So you can think of two galaxies like the Milky Way. So they're merging in a sense that they have been thrown on a collision route. This is a simulation made in a computer. This is not a real image. But these two galaxies are being interacting. So there is a lot of gravity going on over here. So now you see this sort of green light coming out from the center. This light is what comes out of the quasar. So at this point, we have been able to feed the black holes with a lot of matter. So currently, what we expect is that a lot of the quasars that we see in the universe have been fed during galaxy mergers. This is not true for all quasars or for all the accreting black holes, but it seems to be true for a large part of them. So accreting black holes, these quasars, black holes eating food, is a normal phase throughout the evolution of a universe in which galaxies keep on merging. So if you remember the little simulation that I showed of the merging galaxies, the evolution of the cube in the universe, we have seen that galaxies become bigger and bigger because they merge together. So while galaxies merge, also black holes have their share and become larger with time. So now when we go back to this picture, this is again the Chandra Deep Field South. So here what you're seeing is each of these is an AGN, is a quasar. So here we are seeing really the phase in which black holes became quasar. They were eating a lot of material and become as massive as we see them today. So we are connecting the early times to today through this hierarchical evolution of the universe. While galaxies become big, black holes become big as well. And they're shining, and that's good because since they're shining as quasars, we can actually see them. When they're not eating, as I said, unfortunately, they become invisible. So now, what is the other phase in which black holes become visible? Well, they become visible when they're merging. So now we'll move towards something a little more exotic, gravitational waves. So what are gravitational waves? Well, I was told that this slide is kind of scary when the first sentence is gravity is space-time curvature. But this is a simple way of seeing it. So you can think of gravity as a piece of fabric. Our space-time is a piece of fabric. Now, if you're light, well, and everything except for very compact objects is light, when you walk on this piece of fabric, you are not bending it too much. But if you're very heavy, like a black hole, you are bending the piece of fabric. When I hope that Warren doesn't get mad at me, but you see here that the little marbles are not bending much this rubber sheet, but if I put the black hole in the center, the sheet gets bent. So that's what I mean by space-time. Let me do it again. So here we have the black hole is bending space-time. You see the rubber sheet with a hole, but if I'm very light, nothing happens to the rubber sheet. So this is what I mean by space-time curvature. If you are very heavy, very massive, you change the shape of space-time. Now, what is the most catastrophic event in terms of gravity? Two black holes merging together. Two black holes merging together are very, very good at bending space-time, at creating ripples in this space-time. In fact, the black holes merging together will first cause some sort of big hole in the center of this fabric of space-time, and then everything will go back to normal. So here we are looking again at the merger of two galaxies. Now we have zoomed in when the two black holes are approaching each other. So there are two black holes sitting in the center of these two accretion disks. So these are two AGN merging together. You see that black holes are approaching each other. So they're forming a binary. This means that they are bound to orbit each other faster and faster. This is just laws of gravity until, boom, they merge together. You see here that these blue things that are moving away, they're showing you how the black holes are bending space-time, are changing the way space and time move around. This is a higher resolution simulation of the merger of two black holes. So here you see the two black holes in the center, and all these shapes are these gravitational waves, are the way the black holes are modifying the space-time around them. So this is the last phase. The two black holes are merging together. You see how fast they are emitting these waves. And now let's zoom in. This is the merged black hole. So you have formed a more massive black hole, and this black hole is still emitting some of these waves, but slowly it stops because it's not accelerating very fast. We call it ring down. The black hole rings down all the leftover energy, and then it stops and rests. But while these black holes have emitted waves, these waves keep on moving away at the speed of light. So they're stretching space-time as they move until they reach faraway regions. So basically, if we want to detect gravitational waves, what we want to see is the way space-time moves. So up here, you see what we expect to happen if a gravitational wave passes nearby. You see here, it really shows how space is stretched in one direction and then goes back. So one of the ways that we are expecting to detect gravitational waves by looking at how space, if at some point we have space stretched in one direction and then going back. And then you can see it in the other direction. So the experiment that NASA and ESA, NASA is the, what NASA is, and ESA is the European Space Agency. They have got together to think of how they can try and detect these gravitational waves. So their idea was to have, have two mirrors far away and to have a laser send light to a mirror and come back. Now, if you know exactly the distance between the source of the laser and the mirror, you can predict how long it takes for light to be reflected and go back. But if a gravitational wave passes through here, all of a sudden there is more space between your laser and the mirror. So it takes a longer time for the laser for the light to be reflected back. So that's the idea behind detecting gravitational waves. And this is the instrument that is supposed to do that. It's not. It will take a while before it's launched, but the idea is to have lasers shooting at mirrors at a distance of 5 million kilometers. This will happen in space, very far away from Earth. Why do you need lasers to be as distant as 5 million kilometers? This is because although gravitational waves seem to be very powerful, in fact, the way they change space-time is very subtle. In fact, to detect the gravitational waves coming from two merging black holes, like those that I've shown you, you have to be able to make a measurement which is so accurate as if you were standing right here on Earth and you wanted to measure the diameter of a human hair put at the distance of Mars. So that's the technological challenge that we are facing to measure gravitational waves. On the other hand, what is the good thing about all this? Is that we are seeing black holes that are merging. So we are seeing black holes that in principle are not eating matter, that are not necessarily quasar. So we are seeing black holes in a different phase of their evolution. And also, well, we will have a proof that general relativity is right. So it's one of these experiments that it's very hard, but if it works, it's very rewarding. So I hope that I will see all these before I retire. And I hope it will not be too late. But so I think that I've finished my time. So I gave you a little tour of the lives of black holes, starting from a few million years after a Big Bang until today, starting from the seeds all the way to today, and how we can hope to detect black holes today and in the future. Thank you.
Saturday Morning Physics is sponsored by the Physics Department of the University of Michigan, by the Dr. Lois Tiffany Endowment, and by gifts from friends of the program.